You're floating 93 million miles from a nuclear reactor that fuses 600 million tons of hydrogen every single second. Its surface burns at 10,000 degrees Fahrenheit. Its core reaches 15 million degrees. And you are freezing to death, not slowly. Rapidly, brutally. One side of your suit is hot enough to cook food. The other side is cold enough to shatter metal. At the exact same time. How is this possible? How can the most powerful object in our solar system leave the surrounding universe just 2.7 degrees above the coldest temperature that can physically exist? The answer will completely destroy everything your gut tells you about heat and reveal just how impossibly rare our warm little Earth truly is. Why your intuition is lying to you, your entire understanding of heat is wrong. And it's not your fault. Every single thing you know about warmth comes from living at the bottom of a thick ocean of gas. That ocean is our atmosphere, a dense, churning blanket of nitrogen and oxygen molecules wrapped around our planet like an invisible shield. When sunlight pours down on a summer afternoon and you feel that warmth on your skin, you're not just feeling sunlight. You're feeling solar rays slamming into trillions of air molecules above you, causing them to vibrate, collide, and transfer energy in a chaotic chain reaction. Temperature, at its most fundamental level, is simply the speed of molecular movement. Faster molecules equal more heat. Those warmed molecules bumped into you, into the ground, into everything around you. The heat spreads. It lingers after sunset. It follows you into the shade. This is why your brain instinctively expects space near a giant star to be warm. But space isn't filled with air. Space is where air goes to die. The three laws that govern everything physics gives us exactly 3 ways heat can travel from one place to another. 3. No more, no less. Conduction is heat through direct contact. Grab a hot pan, that burning sensation is conduction. Energized molecules in the metal crashing directly into molecules in your skin, passing energy like a relay baton. It requires physical touch. Convection is heat through moving fluid. Boil water and watch the bubbles. Hot water rises. Cooler water sinks, creating currents that distribute heat throughout the pot. Convection drives weather, ocean currents, and wind. It also requires something physical to carry the heat. Radiation is the rule breaker. Heat carried by electromagnetic waves, primarily infrared light, needing absolutely nothing to travel through. No air, no water, no medium whatsoever. It blazes through total emptiness at the speed of light. This is how the sun's energy reaches us at all. Pure radiation, crossing 93 million miles of nothing. Here's the catch that changes everything. Radiation heats matter. It does not heat empty space. Think of a laser pointer in a dark warehouse. If the air is perfectly clear, you see nothing, no beam cutting through darkness. You only see a bright dot where the laser strikes the far wall. The energy traveled the entire length of that warehouse, but didn't illuminate a single cubic inch of air along the way. The sun's radiation works identically. It blazes outward in every direction. It travels through the void in complete silence. And it only transforms into heat when it finally strikes something with mass: a planet, a moon, a grain of dust, an astronaut's visor. The empty space it passes through? Completely untouched. The moon doesn't lie. Our moon is the perfect laboratory for this experiment because it has almost no atmosphere, no air blanket, no molecular ocean to store or share energy. It operates on pure, unfiltered radiation physics. When sunlight strikes the lunar equator, the surface climbs to 250 degrees Fahrenheit, hot enough to boil water. But the moment that same ground rotates into shadow, with no atmosphere to hold the heat, the temperature doesn't drop gradually. It collapses. It plunges to minus 280 degrees Fahrenheit in the darkness. Inside permanently shadowed craters near the lunar poles, places where sunlight hasn't touched the ground in billions of years, NASA has measured temperatures around minus 410 degrees Fahrenheit. some of the coldest naturally occurring places in our entire solar system. On the moon, our neighbor, the object humans once drove a car on, the International Space Station experiences the same brutal reality. The thermosphere it orbits technically contains molecules with tremendous energy thousands of degrees worth. But those molecules are so incredibly spread apart, they almost never collide with the station. They can't transfer their heat. So the sunlit side of the ice bakes at 250 degrees Fahrenheit, while the shadowed side simultaneously drops to minus 250 degrees Fahrenheit. Same spacecraft, same moment, a 500-degree swing from one side to the other. Then there's Mercury, the closest planet to the Sun. With essentially no atmosphere, its daytime surface hits 800 degrees Fahrenheit. Its night side? Minus 290 degrees. The Sun is right there, and Mercury's dark side remains one of the coldest surfaces in the inner solar system. Now compare that to Venus farther from the Sun than Mercury, but wrapped in the thickest, most oppressive atmosphere in our neighborhood. That dense blanket traps heat so aggressively that Venus maintains a constant 900 degrees Fahrenheit everywhere, day and night. Poles and equator, every inch baked identically. Venus is hotter than Mercury, despite being farther from the Sun. The medium matters just as much, arguably more, than the radiation source itself. The temperature of nothing, so what is the actual baseline temperature of the universe when you strip everything away? After the Big Bang, the universe was unimaginably hot and dense. As it expanded over 13.8 billion years, it cooled. That ancient heat didn't vanish, it stretched into longer and longer wavelengths, becoming a faint, uniform microwave glow saturating every cubic inch of the cosmos. Scientists call it the cosmic microwave background. It is the oldest light in existence, the literal echo of creation. And today, that background radiation gives the universe a base temperature of 2.7 Kelvin, approximately minus 455 degrees Fahrenheit. That is the default temperature of reality. That is what the universe looks like when you remove stars, planets, and every other local heat source. Nearly absolute zero. The point at which molecular motion itself grinds to a halt. Space isn't approaching absolute zero. Space essentially is absolute zero with a few small burning exceptions scattered across incomprehensible distances. The real answer so, why is space freezing cold when the Sun burns so ferociously? The Sun isn't failing. It's doing exactly what physics requires, radiating energy in every direction at an almost incomprehensible rate. But heat, real heat, the kind you can feel, the kind that keeps oceans liquid and life alive, is a property of matter. Specifically, it's kinetic energy stored in vibrating, colliding molecules. In the near-perfect vacuum between planets and stars, those molecules essentially don't exist. There is almost nothing there to receive the Sun's energy and convert it into temperature. The Sun's radiation doesn't warm the void any more than a flashlight warms a dark room. The light travels through the darkness perfectly, but the darkness itself remains dark. Space isn't cold the way a winter night is cold. A winter night is cold because air molecules around you are moving slowly. Space is cold because there are almost no molecules at all. It's not a low temperature. It's the near total absence of the thing that creates temperature. The ending that changes everything. Step back and look at what this actually means. Right now, you are living inside a thin, fragile shell of gas clinging to a rock. That shell is roughly 60 miles thick at its most generous measurement. In cosmic terms, it is tissue paper wrapped around a marble. And that tissue paper is the only reason you are warm. Without it, the side of your body facing the Sun would blister. The side facing away would freeze. You would experience both simultaneously, exactly like astronauts in engineered suits, exactly like the Moon, exactly like Mercury. The gentle warmth of an afternoon? The lingering heat of a summer evening after sunset? The fact that you don't freeze the moment you step into shade? Every single bit of it is the result of that thin atmospheric blanket trapping. absorbing, and sharing solar energy in a constant molecular conversation happening all around you, invisibly, every moment of your life. That is not the normal state of the universe. The normal state of the universe is a cold, silent void occasionally punctured by islands of nuclear fire whose energy screams outward across billions of miles and heats almost nothing along the way. The real paradox of the cosmos isn't that space is cold near a star. The paradox is that a small, warm, living planet like ours exists at all, a tiny bubble of the extraordinary, floating in an infinite ocean of cold. Which fact hit you hardest? The moon's 500-degree temperature swing? Or the fact that our atmosphere is the only reason we're alive right now? Drop it in the comments. I read every single one. If this broke your understanding of heat and cold, share it with someone who thinks space is warm because the sun is nearby. Like, subscribe, and hit the notification bell because next time we go somewhere even colder. See you there.